The forest does not ease into the sound, it detonates into it. One moment the canopy breathes quietly under summer heat, and the next it is vibrating, branches trembling with a pressure that feels less like noise and more like a physical force. The air itself seems compressed, as if the landscape has been pulled tight and plucked like a string. This is the arrival of cicadas, insects whose voices are powerful enough to overwrite birdsong, drown wind, and redefine what silence means within their territory. The sound is so intense that it blurs direction and distance, turning the forest into a resonating chamber where every tree trunk becomes part of the instrument. To stand inside it is to realize that this is not background noise. This is biology weaponized through sound. The cicada's volume is not an accident of size or enthusiasm. It is the outcome of one of the most efficient sound-producing mechanisms ever evolved in the insect world. Along the sides of the male cicada's abdomen sit rigid, ribbed membranes called tymbals. These structures do not vibrate gently like vocal cords. They buckle inward with sudden force when powerful muscles contract, then snap back into place as the muscles relax. Each buckle produces a sharp click. On its own, the sound is unimpressive, but cicadas do not click once. They fire these membranes in rapid sequences, hundreds of times per second, creating a rolling cascade of pressure waves. The hollow abdomen amplifies the signal, functioning like a resonance chamber that boosts volume without requiring additional energy. The insect's entire body becomes an acoustic amplifier, tuned by evolution to project sound across open woodland and dense foliage alike. What makes this mechanism truly extraordinary is its efficiency. A cicada weighing less than a paperclip can produce sound levels comparable to heavy machinery at close range. The physics are brutal and elegant. Instead of pushing air gradually, the tymbals displace it suddenly, generating sharp pressure spikes that propagate with minimal loss. The abdomen's internal air sacs reinforce specific frequencies, ensuring the call carries farther than random noise ever could. This is not just loudness for attention. It is precision engineering shaped by millions of years of reproductive competition and environmental filtering. Yet volume alone does not explain why cicadas sing together. The true power of the cicada's voice emerges only when individuals synchronize into a mass chorus. In these moments, the forest becomes saturated with sound, to the point where predators struggle to function normally. Birds that rely on auditory cues to locate prey find themselves overwhelmed. Directionality collapses. The signal-to-noise ratio disintegrates. This phenomenon, known as predator overload, is one of the most ruthless survival strategies in nature. Cicadas do not hide, they flood the system. Mass emergence pushes this strategy to its extreme. In certain species, millions of cicadas rise from the soil simultaneously after years of subterranean development. Their appearance is sudden, overwhelming ecosystems that have not encountered them for more than a decade. Predators gorge themselves to exhaustion, consuming cicadas far beyond normal intake limits, yet barely denting the population. The sheer abundance ensures that most individuals survive long enough to reproduce. Sound plays a critical role here. The chorus is not simply a byproduct of crowding. It is a synchronized broadcast that announces presence, swamps predator senses, and accelerates mating before population numbers inevitably crash again. Within this acoustic chaos, order still exists. The soundscape is structured, layered, and fiercely contested. Cicada calls function as territorial claims, carved not into soil or bark, but into auditory space. Each male occupies a specific frequency range and rhythmic pattern, defending it against rivals. When two males overlap too closely in sound, interference occurs. The calls distort one another, reducing their effectiveness. This triggers escalation. One male may increase tempo, shift pitch slightly, or reposition himself within the canopy to reclaim clarity. Territory in this context is measured not in meters, but in uninterrupted acoustic bandwidth. Females listen from within this dense sound field, filtering through the noise with sensory systems honed for discrimination. Despite the apparent uniformity of the chorus, each species produces a distinct pattern. These patterns are not arbitrary. They are consistent in pulse rate, frequency modulation, and temporal spacing. To the human ear, the difference may be subtle or completely lost, but to a female cicada, it is unmistakable. This is an audio fingerprint, a species-specific signature that prevents wasted reproductive effort. In ecosystems where multiple cicada species emerge simultaneously, these differences are essential. Without them, hybridization would blur genetic boundaries and undermine evolutionary stability. The precision required for this system is astonishing. Cicada auditory organs are tuned narrowly to the frequencies produced by their own species. Neural circuits in the brain act as filters, responding most strongly to familiar rhythms while suppressing irrelevant noise. This allows females to locate suitable mates even within choruses that exceed the loudness threshold of pain for humans. What sounds like chaos is, in biological terms, a carefully partitioned communication network operating at maximum capacity. There is something unsettling about this realization. The noise feels wild and unstructured, yet it is governed by rules as strict as any language. Every pulse conveys information about species identity, physical condition, and location. Males with damaged tymbals or weakened musculature produce distorted calls and are quietly ignored. The chorus becomes a sorting mechanism, amplifying the voices of the fit while silencing the flawed through reproductive exclusion. Natural selection does not need claws or venom here. It listens. The creepiness of the cicada chorus lies in this hidden order. The sound does not respond to human presence. It does not pause or adapt. Walk through a forest at peak emergence, and the noise washes over you without acknowledgement, as if the ecosystem has switched into a different operating mode where mammals are irrelevant. The calls continue long after dusk, merging with heat and humidity into an atmosphere that feels almost alive. It is easy to forget that each note is produced by an individual insect, its abdomen flexing again and again until exhaustion or mating ends the performance. And when mating does occur, sound remains central. Females respond not with song, but with movement, orienting toward preferred calls and closing the distance silently. In some species, they produce subtle wing flicks that create brief acoustic cues, guiding males in the final approach. Even here, precision matters. Mistimed signals are ignored. Incorrect rhythms are rejected. The entire reproductive cycle hinges on timing and pattern, enforced by ears tuned to evolutionary memory. As abruptly as it begins, the chorus fades. Days or weeks later, the forest exhales. The bodies of spent cicadas litter the ground, feeding decomposers and returning nutrients to the soil. Eggs rest in tree branches. Below the surface, newly hatched nymphs drop and burrow, vanishing into darkness for years. The sound is gone, but its effects linger. Predator populations spike and then crash. Trees respond to oviposition scars with new growth. Soil chemistry shifts under the influx of decaying biomass. All of it initiated by insects whose most powerful adaptation is not speed, armor, or venom, but noise. The cicada is a living siren, not because it lures victims, but because it reshapes its environment through sound alone. Its voice defines territory, overwhelms enemies, selects mates, and synchronizes life cycles across landscapes. In a world that often equates power with violence, cicadas offer a different lesson. Sometimes survival is not about striking harder or hiding better. Sometimes it is about being heard so completely that nothing else can compete. The forest floor of Madagascar is a place where light fractures into fragments, where fallen leaves trap moisture and heat, and where sound rarely travels far before being absorbed by soil, bark, and decay. Here, vision is unreliable, shapes dissolve into shadow, movements happen inches away without ever being seen. In this compressed world, survival depends less on speed or camouflage and more on the ability to communicate instantly, decisively, and without ambiguity. This is the environment that shaped one of the most unusual defensive technologies in the insect world. The hiss of the Madagascar cockroach, a sound that functions as warning, dominance signal, and courtship call, all produced without vocal cords, wings, or stridulating limbs. At rest, the cockroach appears almost inert, its armored body pressed low against the substrate, legs tucked beneath overlapping plates that resemble polished stone. Its exoskeleton is thick for an insect, reinforced to resist crushing forces from predators that hunt by bite rather than precision, but this armor alone is not enough. When disturbed, when a shadow moves too quickly or pressure shifts in the leaf litter, the cockroach does not flee immediately. Instead, it weaponizes air. A sudden explosive hiss tears through the stillness, sharp enough to startle even vertebrate predators accustomed to the forest's quiet churn. The sound is brief, forceful, and unmistakably intentional. Unlike insects that generate noise by rubbing body parts together, this cockroach produces sound through forced respiration. Along the sides of its abdomen are spiracles, openings that normally regulate gas exchange, allowing oxygen to diffuse into the tracheal system that delivers air directly to tissues. In the Madagascar cockroach, these spiracles are also valves. When abdominal muscles contract violently, air is expelled through them under pressure, producing a hiss that resembles steam escaping from a ruptured seal. The sound is not a byproduct of breathing faster. It is an active expulsion, driven by muscular control and timing. At the macro scale, the behavior is startling. The body segments visibly compress and rebound. The spiracles flare open for a fraction of a second, then clamp shut again. Each hiss is a controlled discharge, not unlike the release of compressed gas in mechanical systems. The volume is disproportionate to the insect's size, especially in the confined acoustic space beneath leaf litter. Here, sound reflects off roots and stones, amplifying its perceived origin and making it difficult to localize. For predators that rely on close-range strikes, this confusion can be enough to halt an attack. The hiss functions first as intimidation. Many of the cockroach's predators are small mammals, reptiles, or amphibians that associate sudden noise with danger. In a world where most insects remain silent, sound itself becomes a threat signal. The hiss suggests size, aggression, and readiness to resist, even when the insect has no venom and no biting apparatus capable of serious harm. This is bluff, refined into physiology. Natural selection has favored individuals whose hiss triggers hesitation, because hesitation creates opportunity, and opportunity creates survival. But the hiss is not a single signal with a single meaning. It is a flexible system, modulated in duration, intensity, and repetition depending on context. When two males encounter one another in competition for territory or access to females, the hiss changes character. These confrontations are ritualized, rather than immediately violent. The males face off, bodies elevated slightly, antennae probing, each attempting to assess the other's size and stamina. Hissing erupts in bursts, each insect trying to outproduce the other in volume and persistence. The contest is not about causing harm, it is about establishing dominance without risking injury. In this sense, the hiss functions as an acoustic measurement of physical condition. Producing a strong hiss requires powerful abdominal muscles and efficient control of spiracles. Weaker individuals cannot sustain repeated expulsions without fatigue. Over time, the louder, more persistent hissing male claims the contested space, while the subordinate retreats. This conserves energy and reduces injury across the population, a subtle but powerful example of how communication can replace combat in evolutionary systems. The same mechanism is repurposed again during courtship. Females, though capable of hissing defensively, listen closely to male displays. Courtship hisses differ from threat hisses in rhythm and timing. They are longer, more structured, often produced in sequences that advertise stamina rather than aggression. In the darkness of the forest floor, where visual cues are limited to silhouettes and movement, sound becomes the primary channel for mate assessment. A male capable of sustained, controlled hissing demonstrates not only strength but metabolic efficiency, an important trait in an environment where food availability fluctuates. What makes this system especially effective is its integration with the cockroach's broader sensory world. The species is primarily nocturnal, navigating using antennae that sample chemical traces, vibrations, and air currents. The hiss complements these senses by adding a long-range signal that cuts through the clutter of micro-habitats. It is an alarm system in a world without sightlines, broadcasting intent across a radius defined not by vision, but by sound propagation through organic debris. There is an unsettling mechanical quality to the hiss, amplified by its suddenness and volume. It feels less like an animal sound and more like a system malfunction, an auditory warning that something has been breached. This is precisely why it works. Predators do not evolve responses to aesthetics. They evolve responses to consequences. Over time, individuals that ignored hissing insects likely experienced enough negative outcomes to reinforce avoidance. The sound does not need to be truthful. It needs to be consistent. Beyond defense and reproduction, the hiss also plays a role in spacing and social organization. While not truly social insects, Madagascar cockroaches do aggregate in favorable microhabitats where humidity and temperature are stable. In these crowded conditions, low-level hissing helps maintain personal space, reducing physical contact that could lead to stress or injury. The sound becomes a negotiation tool, allowing individuals to assert boundaries without constant movement or confrontation. Thermoregulation weaves subtly into this story as well. The cockroach's large body size for an insect allows it to retain heat, but also requires careful management of respiration to prevent water loss. Spiracle control is therefore already finely tuned for balancing oxygen intake and humidity retention. The evolution of sound production through forced air likely emerged from this pre-existing physiological framework. What began as respiratory regulation was co-opted into communication, demonstrating how new functions often arise from old systems under new pressures. Watching the insect at extreme close range reveals the elegance of this adaptation. Each hiss is accompanied by a visible tightening of the exoskeleton, the plates shifting minutely as muscles contract beneath them. The spiracles open like valves in an engine, releasing air in a precise burst. There is no waste, no randomness. The insect does not scream, it deploys. In the larger ecological context, this behavior reinforces the cockroach's role as a resilient recycler within the forest. By deterring predation efficiently, individuals survive longer, continuing to process decaying plant material and return nutrients to the soil. The hiss indirectly supports the ecosystem by stabilizing populations that contribute to decomposition and nutrient cycling. Even intimidation has downstream effects. The Madagascar cockroach's hiss is not an oddity. It is a reminder that communication in nature does not require complexity of structure, only precision of function. In a world stripped of light and dominated by texture and proximity, sound becomes authority, air becomes weapon, and a creature often dismissed as primitive reveals itself as an engineer of intimidation, mastering physics and physiology to survive in the dark. The first sign is not the bee itself, but the sound. A low metallic vibration rolls through the air, steady and mechanical, closer to the growl of a power tool than the familiar hum of a pollinator passing through a garden. It does not drift. It holds its position, fixed in space, as if anchored to the wood it surrounds. In the warm light of a sun-exposed beam, a carpenter bee hovers inches from a wooden surface, body suspended with unnatural stability, wings blurred into invisibility. The vibration deepens, intensifies, and the wood beneath it seems to resonate in response. This is not flight. This is work. Carpenter bees occupy a niche where strength matters more than delicacy. Unlike many bees that rely on pre-existing cavities or communal nests, carpenter bees excavate their own shelters directly into solid wood. Fence posts, dead tree limbs, exposed beams, and weathered structures become substrates for reproduction. To accomplish this, the bee must overcome the resistance of lignin and cellulose. Materials evolved to resist decay and compression. The solution is not stronger mandibles alone, but vibration applied with precision. The carpenter bee is a living drill, powered by one of the most versatile muscle systems in the insect world. At the core of this system are the indirect flight muscles, massive bundles that occupy much of the thorax. These muscles do not attach directly to the wings. Instead, they deform the exoskeleton itself, alternately compressing and expanding the thoracic box. When the dorsal longitudinal muscles contract, the thorax shortens and the wings snap downward. When the dorsoventral muscles contract, the thorax flattens and the wings flick upward. This indirect mechanism allows for rapid oscillation with minimal neural input, generating wingbeat frequencies far higher than would be possible through direct muscle control. What makes carpenter bees exceptional is their ability to decouple this system from flight entirely. They can activate these muscles without moving their wings, producing intense vibrations while remaining stationary. The thorax shudders, The exoskeleton hums, and the energy is transmitted directly into whatever surface the bee contacts. In wood excavation, the bee braces its mandibles against the substrate and unleashes sustained vibration. The effect is cumulative. Wood fibers fatigue, microfractures propagate, and fine sawdust accumulates beneath the entrance hole. The bee is not cutting in the traditional sense, it is weakening the material through oscillation, then removing it piece by piece. This same vibration system underpins nearly every aspect of the carpenter bee's survival. In defense, the buzz becomes a warning signal that relies on intimidation rather than injury. Carpenter bees are large, visually conspicuous insects, often mistaken for bumblebees, and their size alone draws attention from birds and mammals. When threatened, the bee does not immediately sting. Instead, it hovers aggressively, facing the intruder, and unleashes a sustained buzz that vibrates the air at close range. The sound is loud, harsh, and unmistakably mechanical, suggesting mass and power disproportionate to the insect's actual capacity for harm. Predators interpret this vibration as risk. In the natural world, loud, sustained mechanical sounds are often associated with struggling prey, defensive capability, or aggressive intent. The carpenter bee's buzz exploits this association. Even predators capable of killing the bee may hesitate, recalculating the cost of engagement. That hesitation is often enough. The bee maintains its position, asserting control over space through vibration rather than physical contact. Territory, in this case, is enforced acoustically. The buzz also plays a critical role in feeding. Many flowering plants conceal their pollen within structures that do not readily release it through passive contact. These plants evolved in environments where wind was unreliable and pollinators needed to be selective. Carpenter bees solve this problem through buzz pollination, a technique that turns vibration into a harvesting tool. Landing on a flower, the bee grips the anthers with its legs and activates its flight muscles without flying. The resulting vibration shakes the pollen loose, ejecting it in visible clouds that coat the bee's body. This process is highly efficient. The frequency of the vibration is tuned to the resonant properties of the flower's reproductive structures. Too weak, and the pollen remains trapped. Too strong, and the bee risks damaging the flower or expending unnecessary energy. The carpenter bee's control over its vibration output allows it to exploit plant species inaccessible to less specialized pollinators. In doing so, it occupies a critical ecological role, facilitating reproduction in plants that depend on mechanical stimulation rather than passive visitation. The industrial character of the carpenter bee's buzz is not incidental. It reflects the sheer power density of its muscle system. Relative to body size, the indirect flight muscles generate enormous force, sustained over long periods without overheating. Thermoregulation becomes essential here. Continuous muscle contraction produces heat, and in a sunlit environment, thermal stress can accumulate rapidly. Carpenter bees manage this through behavioral and physiological mechanisms. They adjust duty cycles, alternating between active vibration and brief rest. They orient their bodies to airflow during hovering, increasing convective cooling. In some species, hemolymph circulation helps redistribute heat away from the thorax. This balance between power and temperature defines the limits of their activity. On cool mornings, carpenter bees are among the first pollinators to become active, their muscle contractions generating enough internal heat to raise thoracic temperature above ambient levels. This allows them to fly and work while other insects remain sluggish. On hot afternoons, activity slows, vibrations shorten, and the bees retreat to shaded areas or nest tunnels where temperatures are more stable. Their industrial capacity is matched by careful energy management. Inside the nest, vibration continues to shape survival. As tunnels extend deeper into the wood, the bee constructs brood chambers, separated by partitions of chewed wood pulp. Each chamber houses a single egg provisioned with a pollen and nectar mass. The precision of this architecture depends on the bee's ability to modulate force and vibration. Too much pressure risks collapse. Too little leaves the structure vulnerable to parasites or environmental stress. The nest becomes a product of vibration controlled at a fine scale, a hidden network carved by oscillation rather than cutting. Parasites and predators challenge this system constantly. Wood-boring beetles, parasitic wasps, and fungi all attempt to exploit carpenter bee nests. In response, bees use vibration defensively within the tunnel, generating disturbances that can dislodge or deter intruders. While not always successful, this behavior adds another layer of protection, reinforcing the nest as an active, defended space rather than a passive shelter. Seen through this lens, the carpenter bee is less a pollinator and more a biomechanical specialist. Its wings are not just for flight. Its muscles are not just for movement. Every contraction serves multiple purposes, from excavation and defense to feeding and thermoregulation. The buzz is not incidental noise. It is output, measurable and functional, applied wherever resistance must be overcome. Standing near a nesting site, the sound carries through the wood itself, vibrating beams and posts with a frequency that feels almost engineered. The bee emerges briefly, hovering in place, then disappears back into the tunnel, the vibration fading and returning in cycles. It is tempting to view this as destruction, but the reality is more nuanced. By creating cavities, carpenter bees contribute to habitat complexity. Abandoned nests become refuges for other insects, spiders, and microorganisms. The damage is localized, the ecological benefit distributed. In the end, the carpenter bee's power lies not in aggression or speed, but in controlled force applied through vibration. It is a reminder that evolution often favors versatility over specialization, turning a flight system into a drill, a speaker, a heater, and a tool for harvesting food. In the quiet moments between buzzes, the wood settles, the air stills, and the bee resumes its work. An industrial engine wrapped in chitin, reshaping its world one vibration at a time. The forest floor hums with life, but not with sound. Rain drips from leaves, wind shivers through branches, birds call and vanish, and the ground absorbs it all. Beneath this shifting ceiling of noise, the soil becomes a quieter place, dense and reliable, where information does not travel through air but through matter itself. Here, inside a labyrinth of tunnels carved through clay and root, leafcutter ants run a civilization that does not rely on voices. Their communication moves through vibration, transmitted through legs, jaws, and bodies pressed against the walls of their world. What looks silent from above is, inside the colony, alive with signals. A leafcutter ant tunnel is never still. Workers move continuously, cutting, hauling, grooming, repairing. Leaves enter one end of the system and are reduced, processed, and transformed into fungal substrate deeper inside. Waste exits elsewhere. Air flows slowly through ventilation shafts, engineered by collective behavior. Temperature and humidity remain stable despite external chaos. This stability is not accidental. It is maintained by constant feedback, and that feedback is carried not by sound waves in air, but by mechanical vibrations traveling through soil, leaf fragments, and the bodies of ants themselves. Ants possess no lungs and no vocal cords, but they are not mute. Many species, including leafcutters, produce vibrations through stridulation, rubbing specialized body parts together. In leafcutter ants, a scraper on the abdomen moves across a ridged file near the thorax, producing rapid pulses. These pulses are not meant to be heard in open air. Their true medium is solid ground. When an ant stridulates while in contact with soil or plant material, the vibration spreads outward, carried by the physical structure of the environment. Inside the tunnels, this method is superior to airborne sound in almost every way. Airborne sound dissipates quickly in irregular spaces. It reflects, scatters, and loses coherence. Soil vibrations, by contrast, travel with consistency, maintaining pattern and timing over short distances. For an ant whose world is measured in body lengths rather than meters, this reliability matters. A vibration transmitted through packed earth reaches nearby workers with minimal distortion, regardless of bends, chambers, or obstructions. The colony uses this system constantly. When a worker encounters resistance while cutting leaves, it vibrates its body against the substrate, producing a signal that recruits additional workers to the task. The vibration is localized, directional, and specific. Nearby ants respond immediately, adjusting their movement toward the source without needing to interpret complex chemical trails. In high-traffic zones, where pheromone signals would become muddled, vibration provides clarity. Defense relies heavily on the same principle. When a tunnel wall collapses, when a predator breaches an entrance, or when fungal gardens are disturbed, alarm vibrations ripple through the colony. These signals trigger rapid, coordinated responses. Soldiers move toward the disturbance. Workers reroute traffic. Fungus chambers are sealed or reinforced. The speed of this response depends on how quickly vibration travels through the structure, and the colony's architecture is shaped accordingly. Tunnel walls are compacted to optimize transmission. Chambers connect at angles that preserve mechanical continuity. The colony, in effect, is built to conduct information. Within the fungus gardens, vibration takes on another role. Leafcutter ants do not eat the leaves they harvest. They cultivate a symbiotic fungus that breaks down plant material into digestible nutrients. This fungus is sensitive. Changes in humidity, temperature, or contamination can threaten its growth. Workers tending the garden use subtle vibrations while grooming and manipulating fungal strands. These vibrations may help distribute spores, stimulate growth, or signal the presence of contamination to nearby workers. Though the precise effects are still under study, the behavior suggests that vibration functions not only as communication, but as a tool for managing living infrastructure. The advantage of vibration becomes especially clear in the context of a tropical forest. Above ground, noise is constant and unpredictable. Rainstorms generate overwhelming acoustic interference. Insects, birds, and mammals produce overlapping sounds across a wide range of frequencies. Any signal relying on air would struggle to stand out. Underground, however, the forest is mechanically quieter. Vibrations caused by raindrops or footsteps are dampened by layers of soil. The ants' signals move through a medium that filters out irrelevant noise, preserving the integrity of their messages. This system also scales. A single ant's vibration travels only a short distance, but the colony operates as a network of relays. Ants receiving a signal may respond by generating their own vibrations, extending the message through the tunnels. The result is a distributed communication web where information propagates without a central controller. No ant oversees the colony, yet coordination emerges from countless local interactions mediated by mechanical signals. Seen from this perspective, the colony resembles an industrial machine more than a collection of insects. Leaves enter as raw material. Vibrational signals regulate flow, labor allocation, and emergency response. Waste is expelled. The fungus garden functions as a biological processing unit. Each ant is a component capable of sensing, transmitting, and responding to mechanical input. The system does not think in the way a brain does, but it reacts with speed and coherence that rival engineered networks. Even individual movement is influenced by vibration. Ants walking through tunnels detect subtle differences in substrate vibration caused by traffic patterns ahead. A congested tunnel vibrates differently from an empty one. Workers adjust routes accordingly, reducing collisions and delays. This is not conscious decision-making, but sensory integration. Legs equipped with mechanoreceptors translate vibration into information about colony flow, guiding behavior without the need for visual cues. Predators that attempt to exploit the colony often fail because they cannot interpret this mechanical language. An invading arthropod may trigger alarm vibrations that mobilize defenders faster than the predator can retreat. Larger animals that disturb the soil create low-frequency vibrations that ants detect long before the threat reaches the nest core. In response, entrances are sealed and workers retreat to deeper chambers, sacrificing expendable outer sections to protect the colony's vital systems. The efficiency of vibration-based communication also shapes the colony's energy economy. Producing pheromones is metabolically expensive and slow to dissipate. Vibrations, by contrast, are generated instantly and vanish as soon as the behavior stops. This allows ants to signal briefly and precisely, avoiding long-term confusion. In a densely populated system, clarity saves energy and prevents error. Over evolutionary time, this reliance on vibration has influenced ant morphology and behavior. Body segments are shaped to transmit oscillations effectively. Postures during stridulation maximize contact with the substrate. Tunnel dimensions favor mechanical conduction. The environment and the organism have co-evolved into a single integrated system, optimized for information transfer through matter. To an observer standing above ground, the leafcutter colony is invisible, its communication unheard. Leaves disappear into holes. Soil mounds rise and fall. There is no sound to mark the complexity below. But inside, the ground itself carries meaning. Every vibration is a data packet, every tunnel a cable, every ant both sensor and signal. The colony does not speak, yet it is constantly communicating, running on a network older than electronics and more resilient than wire. In this hidden world, silence is an illusion. The leafcutter ant colony is alive with motion that can be felt rather than heard, a machine built not of metal but of soil, fungus, and chitin. Its power lies not in individual strength, but in the precision of its vibrations, coordinating millions of bodies into a single adaptive system that thrives beneath the noise of the forest above. In the low vegetation of fields, hedgerows, and forest edges, survival unfolds at close range. Leaves overlap, stems sway, and predators hunt not with sweeping views, but with sudden strikes guided by smell, touch, and brief flashes of movement. In this compressed arena, escape routes are limited. There is rarely time to flee. For shield bugs, also known as stink bugs, survival depends on something far more calculated than speed or concealment. They survive by teaching predators lessons they do not forget, using a two-layer defense that links sound and chemistry into a single reinforced warning system. At rest, a shield bug appears almost inert, its body flattened and angular, edges sharply defined like a piece of living armor. The shape is not decorative. The broad, shield-like outline spreads pressure across the exoskeleton, making it harder for a predator's bite to find leverage. Colors vary from leaf green to mottled brown, often blending seamlessly into surrounding foliage. This camouflage delays detection, but it is only the first line of defense. When camouflage fails, the insect does not rely on surprise alone. It escalates deliberately. The escalation begins with sound. When disturbed or grasped, many shield bugs produce short, sharp noises by vibrating their bodies or rubbing specific structures together. The sound is not loud by human standards, but in the immediate sensory world of a predator, it is abrupt and unnatural. Birds, small mammals and reptiles hunting through foliage expect silence or the soft rustle of prey. A sudden click or buzz violates that expectation. It triggers hesitation, a moment of reassessment that buys the insect precious time. This sound is not random. It is a controlled signal, produced consistently across encounters. Over evolutionary time, this consistency has allowed predators to associate the noise with what comes next. Because the sound is paired so reliably with a chemical defense, it becomes meaningful. The noise alone is enough to prime avoidance behavior. In effect, the shield bug is training its predators, using repetition rather than force. If the warning sound fails, the second layer deploys instantly. Glands along the thorax and abdomen release a volatile chemical cocktail into the air and onto the attacker. The smell is sharp, penetrating, and persistent. To human noses, it may resemble rancid herbs, acrid oil, or spoiled citrus. To predators, it is worse. The chemicals irritate sensory membranes, linger on feathers or fur, and contaminate the mouthparts used to capture prey. The taste reinforces the lesson delivered by the sound, sealing the association in memory. This pairing of sound and chemical deterrent is critical. Chemical defenses alone can work, but they often require direct contact, meaning the insect must already be bitten or crushed to be effective. Sound alone may startle, but without consequence it loses credibility. Together, they form a predictive system. The sound announces the chemical defense before it is deployed, allowing predators to abort an attack early. This benefits both sides. The predator avoids an unpleasant experience, and the insect avoids injury or death. Learning plays a central role here. Young birds or inexperienced mammals may attack a shield bug once. They hear the sound, bite, and receive the chemical spray. The experience is memorable. On subsequent encounters, the sound alone is often enough to deter them. This reduces the frequency with which the insect must deploy its chemical reserves, conserving energy and resources. The defense becomes cheaper over time, as predators in the local ecosystem become educated. From an ecological perspective, this system functions much like a burglar alarm paired with pepper spray. The alarm draws attention to the risk, and the spray enforces it. The order matters. An alarm without consequence is ignored. A consequence without warning is costly. Shield bugs integrate both into a single adaptive package. optimized for environments where encounters are frequent and margins for error are thin. The chemistry itself is finely tuned. Shield bug scent glands produce a mixture of aldehydes, hydrocarbons, and other volatile compounds. These chemicals evaporate quickly, forming a cloud that spreads through still air and clings to surfaces. The smell does not merely repel, it interferes with the predator's ability to hunt effectively afterward, masking other scents and creating sensory confusion. For predators that rely heavily on smell or taste, this temporary impairment can be significant. The production and storage of these chemicals come with trade-offs. Synthesizing defensive compounds requires energy and access to specific precursors, often derived from the insect's diet. This ties the effectiveness of the defense to habitat quality and food availability. In nutrient-poor environments, chemical output may be reduced, increasing reliance on the warning sound and armor. In richer environments, the chemical defense becomes more potent, reinforcing the learned association in predators. Shield bug nymphs, smaller and more vulnerable, already possess this dual system, though in reduced form. Even at early stages, they can emit odors and produce subtle vibrations when threatened. This early deployment accelerates predator learning across generations. A bird that learns to avoid a nymph is likely to avoid the adult as well, reinforcing selection pressure in favor of recognizable signals. The effectiveness of the system also depends on consistency. Shield bugs tend to maintain similar body shapes, postures, and behaviors across species, creating a recognizable category of prey. This visual and behavioral uniformity strengthens predator memory. The sound becomes part of a larger pattern that includes shape, movement, and smell. Together, these cues form a warning profile that predators learn to recognize quickly. There is irony in the simplicity of the approach. Shield bugs do not chase predators away or fight back. They do not hide behind speed or venom. Instead, they rely on reputation. The defense works best when it is rarely used, because its power lies in expectation. The insect survives not by winning encounters, but by preventing them. This strategy also influences community dynamics. Predators that learn to avoid shield bugs redirect their hunting efforts toward other prey, subtly reshaping food webs. Shield bugs, in turn, can afford to forage more openly, feeding on plant sap without constant retreat. Their presence affects plant health, nutrient flow, and the distribution of herbivory pressure across ecosystems. A small insect's warning system ripples outward, altering behavior at multiple trophic levels. In close observation, the coordination between sound and chemical release is striking. The body tenses. The exoskeleton vibrates. The sound precedes the spray by a fraction of a second. It is enough. The sequence repeats with remarkable consistency across individuals, suggesting strong genetic control reinforced by selection. Variants that fail to synchronize these elements would have been eliminated quickly. From a human perspective, the defense feels excessive. The smell lingers long after the insect is gone. The sound seems unnecessary once the chemical is released. But evolution does not optimize for elegance. It optimizes for survival. Redundancy is not wasteful when failure means death. In the layered sensory chaos of natural habitats, clarity matters. Shield bugs deliver clarity through a message that predators understand instinctively after only one mistake. The sound says, danger. The smell proves it. Together they transform a soft-bodied, slow-moving insect into an avoided object, protected not by force but by memory. The shield bug does not need to win fights. It needs to be remembered. And in ecosystems where learning can mean the difference between hunger and survival, that memory becomes its strongest armor. On warm stone walls, at the base of sunlit trees, and along the edges of paths where human feet pass daily without noticing, clusters of red and black bodies gather in dense, conspicuous knots. They do not scatter when approached. They do not attempt to hide. Instead, they remain pressed together, layered over one another like spilled embers frozen in place. These are firebugs, insects that have rejected secrecy in favor of visibility and solitude in favor of numbers. What appears at first glance to be careless exposure is, in reality, one of the most calculated survival strategies in the insect world. Firebugs live in open environments where cover is inconsistent and escape routes are limited. They feed primarily on fallen seeds, especially from trees that shed in predictable cycles. These feeding grounds are exposed, often baked by sunlight, and easily patrolled by birds and small mammals. For many insects, this would be a death sentence. For firebugs, it is the foundation of a system built on signaling, aggregation, and shared risk reduction. Their survival does not depend on individual brilliance, but on collective math. The first signal firebugs broadcast is visual. Their coloration is impossible to ignore. Bold red fields, intersected by sharp black patterns, create one of the most recognizable warning displays in temperate ecosystems. This coloration is not camouflage. It is a declaration. Red and black contrast sharply against bark, soil, and stone, ensuring that predators see them clearly and early. This visibility is intentional. Firebugs are chemically defended, containing compounds that make them distasteful to many predators. The color advertises that fact before contact occurs, reducing the likelihood of attack, but color alone is not enough. Warning signals work best when reinforced by experience, and experience is more easily learned when the signal is repeated often and consistently. Firebugs amplify their visual message through aggregation. When dozens or hundreds of individuals cluster together, the warning becomes unavoidable. A predator encountering a group does not see one potential meal. It sees a pattern repeated across space, saturating its visual field. The lesson becomes unmistakable. This grouping behavior is often misinterpreted as a lack of intelligence or an inability to disperse. In reality, it is a response to multiple environmental pressures acting simultaneously. One of the most immediate benefits of aggregation is thermoregulation. Firebugs are ectothermic, relying on external heat sources to regulate their body temperature. By clustering together in sun-exposed areas, they reduce heat loss and stabilize internal temperatures more efficiently than any individual could alone. The bodies of neighboring insects block wind, trap warmth, and create a localized microclimate that allows activity at lower ambient temperatures. This effect is especially important in early spring and late autumn, when sunlight is available but air temperatures fluctuate rapidly. Aggregations allow firebugs to feed, mate, and move during windows that would otherwise be inaccessible. The group functions as a thermal buffer, extending the usable day and season. What looks like idle gathering is, at its core, energy management. The second advantage emerges through predator deterrence. While an individual firebug is chemically protected, it is not invulnerable. Some predators will sample defended prey regardless of warning signals, especially when inexperienced or desperate. In a group, however, the cost to the predator increases dramatically. A bird that pecks into a dense cluster may contact multiple insects at once, receiving a stronger dose of chemical deterrence and reinforcing the aversive experience. The unpleasantness scales with group size. Learning accelerates under these conditions. A predator that makes a mistake with a group is less likely to repeat it. Over time, this creates predator-free zones around habitual aggregation sites. Firebugs benefit collectively from this learned avoidance, even if only a few individuals initially paid the price. The strategy is not altruism, it is statistical survival, where individual risk decreases as group size increases. Short-range communication binds this system together. Firebugs are not silent within their clusters. They exchange information through subtle body movements, tactile contact, and chemical cues released at close range. Antennae brush against neighboring bodies, detecting chemical signatures that convey identity, reproductive status, and readiness to mate. These signals do not travel far. They are designed for density. The group itself becomes the medium. This communication helps synchronize behavior. When temperatures rise enough for movement, individuals begin to disperse almost simultaneously. When conditions worsen, they regroup. During mating periods, aggregations become hubs of interaction where partners are encountered efficiently without the need for long-distance searching. Energy expenditure drops, and reproductive opportunities increase. The street gang comparison is not far off, if stripped of its human connotations. Like a visible group occupying a shared space, firebugs benefit from being seen together. Presence becomes protection. The group sends a message not only to predators, but to the environment itself. This space is claimed. This resource is monitored. This pattern repeats. There is also a mechanical efficiency to grouping. Firebugs feeding on fallen seeds often encounter limited food patches. By aggregating, they reduce the need for constant movement and searching. Individuals feed in proximity, conserving energy. Waste heat from digestion adds marginal warmth to the cluster, further stabilizing conditions. Even inactivity becomes productive when shared. Predator interactions reveal the elegance of this system. Birds approaching a cluster often hesitate, tilting their heads, reassessing. Some peck once and retreat immediately, wiping their beaks or shaking their heads. Others avoid the area entirely after previous encounters. The firebugs do not flee during these moments. They remain still, letting the signal do its work. Movement would only break the visual pattern and introduce uncertainty. Stillness preserves clarity. This reliance on learned avoidance also shapes the bug's life cycle. Firebugs tend to return to the same aggregation sites year after year, reinforcing predator memory across seasons. Young predators learn from older individuals, either through direct experience or social cues, to avoid these clusters. The environment itself becomes conditioned. Aggregation also reduces individual exposure to parasites and environmental hazards in some contexts. While dense groups can facilitate disease transmission, firebugs mitigate this risk through periodic dispersal and the chemical properties of their bodies, which inhibit some pathogens. The balance between risk and reward is finely tuned, adjusted through behavior rather than physiology alone. From above, the group appears chaotic. From within, it is ordered. Individuals adjust position constantly, responding to micro changes in temperature, light, and contact. No central authority directs this movement. It emerges from simple rules applied repeatedly. Move toward warmth, remain near conspecifics, respond to chemical cues, avoid unnecessary exposure. The result is a dynamic system that adapts minute by minute without planning or foresight. This is biological math in action. Each individual follows rules that maximize its own survival probability. Aggregation increases the denominator, reducing per capita risk. Thermoregulation reduces energy costs. Predator deterrence reduces mortality. Communication reduces wasted effort. Together, these effects compound. Firebugs succeed not because they are fast or hidden, but because they are predictable. Their visibility is their strength. Their grouping is their shield. In an ecosystem where noise and motion attract attention, they embrace attention on their own terms, shaping how they are perceived and remembered. To a passing human, the cluster is a curiosity, a splash of color against stone. To a predator, it is a warning sign reinforced by experience. To the firebugs themselves, it is infrastructure, a living network of bodies exchanging heat, information, and risk. The street corner gathering dissolves as the day warms. Individuals peel away, moving toward feeding sites, mating partners, or new aggregation points. By evening, the cluster reforms, reassembling with mechanical inevitability. Nothing about this is accidental. Every body in the group represents a calculation that has been tested across generations. Firebugs do not survive by avoiding attention. They survive by mastering it, turning public presence into private advantage. In doing so, they demonstrate that sometimes the safest place in nature is not hidden away, but standing openly among many, where the message is loud enough that it does not need to be spoken. A leaf is never still. Even on calm days, it flexes under thermal expansion, shifts as moisture evaporates, and transmits the faint tremors of distant movement through its veins. To most animals, these micro-disturbances are meaningless noise. To a jumping spider, they are data. Perched at the edge of a sunlit surface, body compact and elevated on short, powerful legs, the spider pauses, not because it hesitates, but because it is listening through its feet. Jumping spiders do not build webs to wait for prey. They hunt. Their world is measured in angles, distances, and timing, and every successful strike begins long before the leap itself. Vision plays the starring role. Their forward-facing principal eyes are large relative to body size, capable of resolving fine detail and depth at close range. Unlike the diffuse, motion-oriented vision of many insects, jumping spiders see in high resolution, tracking shape, color, and movement with precision that rivals much larger animals. But vision alone is not enough in a cluttered environment where leaves overlap, shadows shift, and light constantly changes. To compensate, jumping spiders integrate a second sensory channel that rarely announces itself: vibration. The surfaces they hunt upon act as information highways. Every step taken by an insect, every wing beat landing, every antenna brushing against a stem sends a ripple through the substrate. These vibrations propagate outward, attenuated by material and distance, but carrying distinct signatures. A beetle walking produces a different pattern than an ant running or a fly grooming its wings. Jumping spiders are equipped with specialized sensory hairs and slit-like organs embedded in their exoskeleton that detect these mechanical signals with extraordinary sensitivity. Legs pressed against a surface become antennae, translating vibration into spatial awareness. The integration of vision and vibration is where the spider's advantage becomes unsettling. When prey enters the field of view, the spider does not simply lock on visually and charge. It remains still, gathering information. Subtle vibrations confirm the prey's position, orientation, and movement rhythm. If the prey stops moving visually but continues to generate vibrations, the spider knows it is still there. If the visual signal flickers due to shadow, but vibrations persist, the spider adjusts its aim. This redundancy allows the hunter to maintain awareness even when one channel is compromised. The process resembles triangulation. Vision provides direction and approximate distance. Vibration refines that estimate, revealing depth through amplitude and timing differences between legs. The spider shifts its body slightly, not to get closer, but to sample the substrate from a new angle, improving its internal model of the scene. Each adjustment updates the calculation. By the time the spider commits to the leap, the outcome is no longer a gamble. It is a solution. This precision matters because jumping spiders commit fully when they strike. They do not lunge repeatedly or chase across long distances. The leap is explosive and terminal. Once launched, the spider cannot correct its trajectory. Missing the target wastes energy and risks exposure to predators. Selection has therefore favored individuals that minimize uncertainty before acting. Waiting is not indecision. Waiting is computation. Vibration also reveals threats. Larger animals moving nearby generate low-frequency disturbances that ripple across surfaces long before shadows or shapes become visible. A bird landing on a branch transmits a distinct signal through connected leaves. A mammal brushing past vegetation sends waves through stems and soil. The spider detects these early warnings and freezes, reducing visual and vibrational output. Remaining motionless is often enough to avoid detection. If the disturbance grows closer, the spider retreats or drops on a silk line, vanishing below the surface plane before the predator arrives. The silk line itself is part of the system. Every jumping spider anchors a drag line before moving. This line is not only a safety tether, it also transmits vibration back to the spider, extending its sensory reach. Tension changes in the line indicate air movement or contact elsewhere. The spider's environment becomes a network of connected surfaces, each capable of delivering information. Vision dominates the foreground of this experience, and it is here that the creep factor becomes unavoidable. Jumping spiders do not glance. They stare. Their large anterior eyes track objects smoothly, adjusting focus and angle in ways that feel intentional. When a human leans close, the spider turns to face the movement, eyes reflecting light like polished glass. It does not flee immediately. It assesses. The posture is unmistakably predatory, despite the size mismatch. This behavior is not curiosity in the human sense, but evaluation. The spider is determining whether the moving shape is prey, predator, or irrelevant background. Vibrations from footsteps or shifting ground contribute to this assessment. A stationary observer produces fewer useful signals than a walking one. The spider integrates both channels and decides. In hunting scenarios, this integration allows jumping spiders to exploit prey that would otherwise be difficult to capture. Fast-moving insects that rely on visual camouflage can be detected through their vibrations. Prey hidden behind obstacles can be tracked indirectly. The spider may reposition itself not to maintain line of sight, but to improve vibrational clarity. Leaves act as membranes, stems as conduits, bark as resonators. Each material alters signal transmission in predictable ways, and the spider's nervous system is tuned to interpret those differences. Research has shown that jumping spiders can distinguish between biologically relevant vibrations and background noise. Wind-induced movement produces broad, irregular patterns. Insect locomotion produces rhythmic, patterned signals. The spider filters accordingly, ignoring irrelevant disturbances while focusing on those that match prey profiles. This selectivity reduces false positives and conserves energy. The leap itself is a mechanical marvel. Hydraulic pressure generated by internal fluid shifts, extends the legs explosively, launching the spider forward with acceleration sufficient to cross many body lengths in a fraction of a second. The trajectory is pre-computed, the landing zone is chosen, the spider strikes with forelegs extended, fangs ready, venom delivered immediately. There is no struggle, the prey is subdued almost instantly. From an ecological perspective, jumping spiders play a stabilizing role in many habitats. They prey on a wide range of insects, including agricultural pests, and do so without constructing webs that could interfere with pollinators or other beneficial species. Their hunting style is selective and responsive, driven by real-time assessment rather than passive capture. This reduces unintended bycatch and allows the spider to adapt to changing prey availability. Their presence also influences the behavior of other arthropods. Insects capable of detecting vibration may alter movement patterns in areas frequented by jumping spiders, reducing activity on exposed surfaces. This creates a mosaic of micro-habitats shaped by predator pressure, influencing where insects feed, mate, and rest. The spider's impact extends beyond the individuals it captures. Thermoregulation intersects with this sensory strategy as well. Jumping spiders rely on sunlight to maintain activity levels, often positioning themselves in warm patches that enhance muscle performance and reaction time. Heat also affects vibration transmission. Warmer materials transmit vibrations differently than cooler ones, subtly altering signal properties. The spider's preference for sunlit surfaces may therefore enhance both motor and sensory performance, aligning physiology with perception. There is something unsettling about a predator that waits, watches, and calculates at such a small scale. The jumping spider does not rely on brute force or traps. It relies on awareness. It reads the world through multiple channels simultaneously, constructing a dynamic map of its surroundings. This map updates continuously, guiding decisions that appear almost deliberate. To witness this is to be reminded that intelligence in nature is not defined by brain size alone. It emerges from the integration of sensory input, motor capability, and ecological context. The jumping spider's brain is tiny, yet it supports behaviors that mirror those of much larger hunters. It stalks, pauses, repositions, and strikes with purpose. When it turns to face you, eyes fixed and unblinking, the sensation is difficult to dismiss. You are not just being seen, you are being measured. The spider is aware of your movement, your vibration, your presence within its environment. It may decide you are irrelevant, or it may retreat. Either way, the decision is informed. In the end, the jumping spider's power lies in its refusal to commit blindly. It does not rush. It listens through its feet, watches through its eyes, and waits until the equations resolve. In a world built of trembling surfaces and shifting light, it has become a master interpreter, turning vibration into certainty and vision into action. The leap is only the final punctuation mark in a sentence written long before you ever notice it. In the still air of a forest clearing, the web appears first as a distortion, a shimmer that bends light rather than blocks it. Sunlight fractures across threads so fine they seem almost imaginary, yet arranged with deliberate geometry. At the center waits the golden silk orb weaver, legs extended lightly against radial lines, body suspended in a posture that suggests rest. But nothing about this spider is idle. The web beneath it is not a net. It is an instrument, tensioned, tuned, and constantly monitored, translating vibration into meaning. Every strand of the web carries information. Wind brushes the outer spirals and sends faint tremors inward. Leaves falling nearby produce broad, low-frequency disturbances that ripple briefly and fade. Insects striking the web generate sharp, complex signals that race along silk pathways toward the hub. To the spider, these are not random disturbances. They are signatures. The web is a sensory array spread across space, converting mechanical energy into a readable pattern of movement. Golden silk orb weavers rely on this system because vision is unreliable at the scale and context in which they hunt. Their eyes detect light and movement, but fine detail dissolves quickly in cluttered vegetation and shifting shadows. The web compensates by extending the spider's perception outward, turning empty air into a mapped territory where any intrusion announces itself instantly. The spider does not need to see prey, it needs to feel it, through silk stretched into precise tension. Silk is not uniform. Different threads within the web serve different functions, and each transmits vibration in a distinct way. Radial threads act like straight cables, carrying signals rapidly toward the center with minimal loss. Spiral capture threads are coated with adhesive droplets and are more elastic, absorbing energy and altering vibration frequency. This variation allows the spider to extract information about what has contacted the web and where. When an insect strikes the web, the initial impact produces a burst of high-frequency vibration. The pattern that follows depends on the insect's size, wing structure, and behavior. A flying insect trapped in adhesive silk struggles violently, producing irregular, rapid oscillations that pulse along multiple strands. A heavier insect generates slower, deeper vibrations that travel farther but with less complexity. A leaf or debris produces a broad, dull disturbance that lacks rhythmic structure and dissipates quickly. The spider distinguishes these patterns instinctively. It does not respond to every vibration with equal urgency. A mosquito-sized insect triggers a measured approach. A large, powerful insect elicits caution, sometimes prompting the spider to immobilize from a distance with silk rather than risking close contact. Non-prey signals are ignored entirely. The web filters the world, allowing only biologically relevant information to command attention. This discrimination depends heavily on tension. The spider actively adjusts the web's mechanical properties throughout its lifespan. By tightening or loosening specific strands, it changes how vibrations propagate. Higher tension increases signal speed and clarity, but reduces elasticity, increasing the risk of structural failure under heavy impact. Lower tension dampens vibrations, filtering out background noise, but potentially obscuring subtle prey signals. The spider constantly negotiates this trade-off, retuning the web as conditions change. Temperature plays a role here as well. Silk properties shift with heat and humidity. On warm, dry days, silk becomes stiffer, transmitting vibrations more efficiently. On cool or humid days, elasticity increases, altering signal transmission. The spider compensates by adjusting tension, restoring clarity. This is not a static construction. It is a responsive system maintained through continuous fine-scale modification. At the hub, the spider's legs act as sensors. Tiny hairs and slit organs detect minute movements in the silk, converting mechanical displacement into neural signals. Each leg contacts multiple strands, allowing the spider to compare timing and amplitude across different pathways. This comparison enables localization. The spider knows not only that something has hit the web, but where it is and how it is behaving. The effect is similar to triangulation. Vibrations arriving at one leg before another indicate direction. Differences in intensity suggest distance and mass. The spider builds an internal model of the event, updating it as the vibration pattern evolves. If the prey struggles more violently, urgency increases. If movement slows, the spider may delay, conserving energy or avoiding danger. This caution is necessary because the web captures more than food. It can ensnare predators or dangerous prey capable of injuring the spider. Large wasps, birds, or lizards can tear through silk easily, and approaching blindly would be fatal. The spider reads warning signs in the vibration pattern, recognizing excessive force or irregular movement that signals risk. In such cases, it may retreat to the edge of the web or drop entirely, abandoning the structure rather than gambling its life. The musical analogy is not metaphorical. The web behaves like a stringed instrument under tension. Each strand vibrates at characteristic frequencies determined by length, thickness, and tension. When disturbed, these strands resonate, producing patterns that interact across the web's geometry. The spider is both musician and audience, constantly listening to the performance of its own construction. This design also allows the spider to remain energetically efficient. Rather than patrolling or actively hunting, it lets the web do the work of detection. Energy expenditure is front-loaded into construction and maintenance. Once built, the web provides continuous sensory coverage with minimal metabolic cost. This efficiency supports large body size and prolonged survival in environments where prey availability fluctuates. The golden silk itself adds another layer of function. Its distinctive coloration may reduce visibility to insects by blending with sunlight patterns, increasing capture success. At the same time, the silk's strength allows the web to withstand repeated impacts without catastrophic failure. Stronger silk transmits vibrations more cleanly, preserving signal fidelity even after multiple repairs. Repair is constant. Each night or after damage, the spider replaces broken strands, re-establishing tension and geometry. These repairs are not merely structural, they recalibrate the sensory network. A freshly built web has different vibrational properties than an old one weighed down by debris. By rebuilding, the spider resets its instrument, restoring sensitivity. Predator interactions underscore the system's sophistication. Birds that blunder into webs generate massive disturbances that propagate instantly. The spider detects these signals before visual contact and often escapes by dropping on a dragline. Some predators learn to avoid webs entirely, recognizing the shimmer or the location of habitual constructions. Others exploit them, stealing prey. In these cases, the spider may alter web placement or tension patterns, adapting to local pressure. The web's influence extends beyond the spider itself. By capturing flying insects, it alters insect movement patterns in the area. Pollinators adjust flight paths. Herbivores are removed. Nutrient flow shifts as captured prey is consumed and waste products fall to the forest floor. The web becomes a node in the ecosystem, shaping interactions across multiple scales. From a human perspective, the sight of the web vibrating is mesmerizing. Strands quiver like plucked strings, oscillations racing inward toward the waiting spider. What looks delicate is, in function, precise and robust. The web does not passively wait, it listens. The spider's response when it comes is decisive. Guided by vibration alone, it moves unerringly to the source, navigating along radial lines with minimal hesitation. The prey is located, assessed, and subdued. If venom is delivered, it is targeted. If silk is applied, it is done strategically, limiting movement before approach. Each action is informed by the ongoing vibration pattern, which continues to update until the prey is immobilized. There is something profoundly unsettling in this reliance on unseen signals. The spider does not need to look. It knows. The web extends its senses far beyond its body, turning empty space into a readable surface. Every movement announces itself. Silence becomes safety. Motion becomes vulnerability. In this way, the golden silk orb weaver exemplifies a different model of perception. Instead of seeking the world, it lets the world come to it, translated through tensioned silk into information. The web is not a trap sprung by chance. It is a finely tuned instrument, played continuously by the environment itself. As dusk settles and light fades, the web remains active. Vibrations do not depend on sight. Night-flying insects strike strands they cannot see, sending signals through darkness. The spider responds with the same precision as in daylight. The instrument does not sleep. By morning, dew beads along the silk, adding mass and altering tension. Vibrations change. The spider adjusts. The instrument is retuned once again. The golden silk orb weaver survives not through speed or aggression, but through interpretation. It has turned architecture into perception, silk into soundless music, and space into a readable score. Every vibration is a note. Every note carries meaning, and at the center of it all, the spider waits, listening to a world that never stops playing. The web appears first as a contradiction. Against the muted greens and browns of meadowgrass, a bold white zigzag slices through empty air, thick enough to catch the eye even at a distance. It does not hide, it announces itself. At the center of this structure sits the wasp spider, its body banded in yellow and black, legs splayed symmetrically like the spokes of a wheel. Nothing about this arrangement suggests accident. This is not a trap designed to disappear into the background. It is signage, suspended in space, engineered to be noticed. The stabilimentum, the name given to this conspicuous silk decoration, is one of the most debated structures in arachnology. It serves no obvious mechanical purpose in capturing prey. It does not add strength to the web in any meaningful way, nor does it directly restrain insects. And yet, generation after generation, wasp spiders invest time and energy into constructing it. The reason lies not in physics alone, but in perception. The stabilimentum is a tool for manipulating how other animals interpret space. To understand its function, one must consider the visual world of insects and predators alike. Many flying insects navigate using polarized light patterns, contrasts, and ultraviolet cues. The stabilimentum reflects light differently from surrounding vegetation, creating a high contrast marker that stands out against chaotic backgrounds. For some insects, this signal may resemble a gap in vegetation, a safe passage rather than an obstacle. Drawn toward the bright pattern, they fly directly into the web's capture spiral, only realizing the deception too late. For other animals, particularly birds, the same signal may serve the opposite function. Birds flying through dense grassland are at risk of colliding with webs that can entangle feathers or damage wings. A visible zigzag acts as a warning, reducing accidental destruction of the web and injury to the bird. From this perspective, the stabilimentum protects the spider by advertising the web's presence, encouraging large animals to steer clear. The spider survives not by hiding, but by clearly marking its territory. This duality lies at the heart of the stabilimentum debate. Is it a lure, a warning, or a form of camouflage? The answer appears to be all three, depending on who is looking. The wasp spider does not design its signage for a single audience. It designs for a crowded visual ecosystem where perception varies across species. What attracts prey may deter predators. What confuses insects may clarify hazards for birds. The web operates as a multi-layer signal, interpreted differently by different eyes. Camouflage enters the equation in a subtler way. Against the bright stabilimentum, the spider's striped body can become harder to distinguish. The bold zigzag breaks up the outline of the spider, drawing attention away from its exact position. To an insect approaching at speed, the contrast may overwhelm finer details, delaying recognition of the spider itself. The decoration becomes a form of disruptive background, masking the predator in plain sight. Construction of the stabilimentum is deliberate and precise. After the web's main structure is complete, the spider adds the decoration using dense, opaque silk laid in a zigzag or cross pattern. The shape and size vary between individuals and even between webs built by the same spider on different days. Environmental conditions matter. Light intensity, vegetation density, and prey availability all influence how prominent the decoration becomes. The spider adjusts its signage to context, suggesting a level of behavioral flexibility rather than rigid instinct. This flexibility extends to daily rhythms. Some wasp spiders construct stabilimenta only at certain times of day, when prey activity peaks or when sunlight angles maximize visibility. Others reduce or omit the decoration under conditions of high predation risk, when being too visible could attract unwanted attention. The web is not static advertising, it is adaptive design, revised as conditions change. Predator interactions highlight the stabilimentum's protective role. Birds that have learned to associate the zigzag pattern with an obstacle avoid the area entirely, sparing both web and spider. In regions where bird pressure is high, stabilimenta tend to be more pronounced. In areas dominated by insect prey with strong visual attraction to contrast, the patterns may be finer, tuned to lure rather than warn. This variation across populations suggests that the stabilimentum is shaped by local ecological pressures, refined by selection acting on perception itself. The spider's own coloration reinforces this strategy. The wasp spider's yellow and black bands echo the warning colors of stinging insects. This resemblance is not superficial. Many predators hesitate when confronted with such patterns, associating them with pain or unpleasant encounters. The spider benefits from this hesitation, even though it lacks a sting capable of harming large animals. The stabilimentum amplifies this effect, framing the spider within a visual context that reinforces the warning signal. From the insect's perspective, the deception is more insidious. Flying insects process visual information rapidly, but with limited resolution. The stabilimentum's brightness can override finer detection of silk strands, creating a false sense of open space. Some studies suggest that insects may mistake the decoration for reflected light off vegetation or water, cues that guide flight paths. By exploiting these biases, the spider turns the prey's navigation system against itself. Once contact occurs, vibration takes over. The web transmits the impact instantly, and the spider responds without hesitation. The stabilimentum's job is done. Its role was never to restrain or kill. It was to shape perception long enough for physics and venom to finish the process. The elegance of the system lies in this division of labor between signal and structure. The cost of producing stabilimenta is real. Dense silk requires protein and energy, resources that could otherwise be invested in reproduction or growth. That the spider continues to build them suggests the benefits outweigh the costs. In environments where prey is scarce or predation pressure is intense, even small advantages in detection or avoidance can determine survival. The stabilimentum persists because it works often enough to matter. There is an architectural quality to the web that reinforces the impression of design. The zigzag does not float randomly. It aligns with the web's radial lines, integrated into the overall geometry. The spider positions itself at the center, legs arranged symmetrically, becoming part of the visual composition. The entire structure reads as intentional, like signage placed at the focal point of a public space. Seen through this lens, the wasp spider is not merely a predator, but a visual engineer. It manipulates contrast, symmetry, and expectation. It understands through evolution rather than cognition how different animals read space. The web becomes a billboard that advertises danger to some and opportunity to others, all while concealing the true nature of what waits at its center. The irony is that the spider itself does not move while the message does its work. It remains still, trusting the design to perform. Movement would only introduce uncertainty. Stillness preserves the illusion. The web speaks on the spider's behalf. As sunlight shifts and wind moves grass around the web, the stabilimentum remains fixed, a bright slash against a restless background. Insects approach, birds veer away, the spider waits. The effectiveness of the system is revealed not in dramatic action, but in the absence of it. Webs remain intact, prey continues to arrive, predators pass by. In a landscape crowded with signals, the wasp spider has carved out a visual language that cuts through noise. It does not shout, it displays, it does not chase, it convinces. The stabilimentum is not decoration for decoration's sake. It is strategy rendered in silk. What appears to be a simple zigzag is, in reality, a negotiation with perception itself. A line drawn in air that means different things to different eyes. A warning sign, a lure, a disguise, depending on who is reading it. The wasp spider survives not by overwhelming force, but by designing the message before the encounter ever happens. The sound arrives before the animal resolves into form. A steady, high-pitched hum cuts through the still air of late afternoon, distinct from the erratic buzz of bees or the flutter of butterflies. It holds its pitch, unwavering, as if generated by a machine rather than a living body. Then, suspended in front of a flower without ever touching it, the hummingbird hawk moth appears. Wings reduced to a translucent blur, body locked in place with improbable stability. Insects are not meant to do this, and yet, here it is, hovering with a level of control that seems to ignore the constraints of size, air, and muscle. This precision is not cosmetic. It is survival distilled into motion. The hummingbird hawk moth lives in an ecological niche defined by speed, exposure, and competition. Flowers that provide its nectar are often open, isolated, and visible to predators. Landing would slow the insect, anchoring it to a predictable point in space. Instead, the moth feeds on the wing, extending its long proboscis deep into the flower while maintaining a constant hover. The result is a feeding strategy that minimizes vulnerability and maximizes escape potential. Hovering at this level requires extreme biomechanical coordination. The moth's wings beat at a frequency far higher than most insects of comparable size, producing the characteristic humming sound that gives the species its name. Each wing stroke generates lift not only on the downstroke, but also on the upstroke, through precise changes in wing angle and rotation. This creates a continuous lifting force, smoothing out fluctuations that would otherwise cause the insect to bob or drift. Unlike gliding or forward flight, hovering offers no aerodynamic shortcuts. There is no momentum to exploit, no airflow to lean into. Every millisecond of lift must be actively generated. The moth's flight muscles operate near their physiological limits, contracting and relaxing with relentless regularity. Energy expenditure is enormous. To sustain this, the moth relies on a rapid metabolic turnover fueled by nectar rich in sugars. Feeding is not just nourishment, it is refueling in real time. The sound of the wings is a byproduct of this intensity. Air is pushed downward and outward in tightly controlled vortices, creating pressure waves that register as a hum. Unlike the irregular buzzing of insects that flap inefficiently, this sound is stable, almost tonal, reflecting the consistency of the wing beat. To predators, the noise can be confusing. It does not match the auditory profile of typical prey. To humans, it suggests machinery. Stability is maintained through constant sensory feedback. The moth's compound eyes track visual references in the environment, locking onto flower edges, stems, and surrounding vegetation. Even slight shifts in position are detected and corrected instantly. Antennae contribute as well, acting as gyroscopic sensors that detect changes in body orientation. Experiments have shown that damage to the antennae severely compromises hovering ability, underscoring their role in balance and control. Airflow itself becomes a source of information. As the wings move, they create a self-generated wind field around the body. Changes in this airflow, caused by gusts or obstacles, alter pressure patterns across the moth's sensory hairs. These changes feed back into the flight control system, prompting rapid adjustments. The moth is not merely reacting visually, it is feeling the air it manipulates. This level of control allows the hummingbird hawk moth to feed from flowers that exclude other insects. Deep corolla tubes, narrow openings, and delicate structures that cannot support weight become accessible. The long proboscis, coiled beneath the head when not in use, unspools smoothly and precisely, guided into the flower while the body remains stationary. Nectar extraction happens without contact, reducing wear on the flower and avoiding entanglement. The ecological consequences are significant. By feeding while hovering, the moth can visit a wide range of flowers quickly, transferring pollen between plants separated by distance. Its mobility allows it to exploit transient resources, moving across landscapes as blooms appear and fade. This nomadic behavior is supported by impressive navigational ability. The moth is capable of long-distance movement, adjusting activity patterns to temperature and light conditions. Thermoregulation plays a crucial role here. Hovering generates heat rapidly, both from muscle activity and from air friction. The moth must balance heat production with dissipation to avoid overheating. It achieves this through controlled pauses, adjusting wing beat frequency and orienting its body to airflow. On cooler days, the intense muscle activity allows the moth to remain active when other insects are grounded. On hot days, activity is shifted to cooler hours. Predators face a difficult challenge when confronting such a target. Birds attempting to capture the moth must contend with its speed, unpredictability, and constant readiness to flee. The moth does not need to disengage from a perch. It simply accelerates from hover into forward flight in an instant. The same muscle system that maintains position can redirect force horizontally, converting lift into thrust with minimal delay. The hummingbird comparison is unavoidable, but it is also misleading. Birds and insects arrived at hovering flight through entirely different evolutionary paths. Birds rely on skeletal muscle attached directly to wings with feathers acting as airfoils. The moth uses an exoskeleton and indirect muscle action, deforming the thorax to move wings. Despite these differences, the outcome converges. Stable hover, precise control, and the ability to feed without landing. This is convergent evolution, driven by the demands of exploiting flowers while avoiding danger. The hum itself may provide an additional benefit. Some predators use auditory cues to locate prey. The steady tone of the moth's wings may be harder to localize than the intermittent sounds of flapping insects. Directionality becomes ambiguous, buying the moth fractions of a second that can determine escape. Whether this is an evolved feature or a byproduct of efficient flight remains uncertain, but its effect is real. From a human perspective, The resemblance to a small drone is striking. The moth holds position relative to a flower, even as wind shifts petals and stems. It compensates continuously, maintaining distance and alignment. Modern hovering drones rely on sensors, processors, and algorithms to achieve similar stability. The moth accomplishes this with a nervous system smaller than a grain of rice, using biological hardware refined over millions of years. The comparison highlights a deeper truth. Stable hovering is not trivial. It requires constant correction and energy input. Nature solved this problem long before engineering did, using flexible wings, rapid feedback, and integrated sensory systems. The hummingbird hawk moth embodies this solution in its purest form, a flying organism that treats air as both medium and signal. As dusk approaches, activity does not cease immediately. The moth continues to feed in low light, guided by memory and residual visual cues. Its hovering remains steady even as contrast fades. When it finally departs, the hum diminishes smoothly, not abruptly, as the insect accelerates away, disappearing into vegetation with barely a trace. The flower remains, gently swaying, nectar reduced, pollen redistributed. The interaction lasted seconds, but its impact extends far beyond the moment. Pollination patterns shift, energy moves through the ecosystem. A predator was avoided, all of it hinged on the ability to hover. In the end, the hummingbird hawk moth is not remarkable because it resembles a bird or a machine. It is remarkable because it demonstrates that control, precision, and efficiency are not the exclusive domain of large brains or complex technology. In a body light enough to be lifted by a breath of wind, nature built a flight system capable of holding space itself. Long before humans imagined hovering drones, this insect mastered the art of staying still in a moving world. And every time its wings hum in place before a flower, it reminds us that innovation is not new. It has simply been flying past us, unnoticed, all along.